In junior high school, you learn Newton's third law in the following way. For every action, there's an equal and opposite reaction. And that's a correct statement of Newton's third law. If you stated it that way on a quiz or a test, I would absolutely mark that correct. But that's not the way that I like to state it. I don't think it's the best way, even though it's a correct way. I like to state it in the way that it's up on the board right now. It says, if object A applies a force on object B, then object B applies an equal and opposite force on object A. It's the same law. But if we state it the way that you learn it in junior high school, for every action there's an equal and opposite reaction, what we tend to think is that the forces balance and cancel out. So let's say person A applies a force on person B of 100 newtons. Well, there's an equal and opposite force of 100 newtons in the opposite direction. 100 plus negative 100 is 0. The net force is 0. They cancel out. Well, that doesn't happen. Sometimes we get a net force of 0, but not because of equal and opposite forces, not because of Newton's third law. When I apply a force on object 2, on object 1, I apply a force on object 2, that object 2 applies an equal and opposite force on me. We're talking about two separate objects, so those equal and opposite forces do not balance out. If we state it this way, we're more likely to remember that we're dealing with two different objects, and therefore we have a net force acting on both of them. I push on object 2 pushes on me, object 2 accelerates, so do I. We both accelerate as a result of this net force. Now, not necessarily at the same rate. The force will be the same always. The acceleration will be different because the acceleration depends upon the mass. Okay, if I push on object 2 and object 2 is heavier than I am, then object 2 will accelerate backwards, but with an acceleration that's less than my acceleration. All right, we got 3 examples here that we went over on Friday, but we'll go through them quickly again here. We talked about object 1 and object 2, or object A and object B, and the action forces, reaction forces. They're not usually that hard to identify. The action force is the first force that we have. In this case, when a hand pushes on the wall, the action force is the hand on the wall. What's the reaction force? If the hand pushes on the wall, then the wall pushes on the hand. Seems kind of hard to believe that the wall pushes on my hand. But if I lean against the wall like this, if I lean against the wall like this at an angle of, let's say, 20 degrees, the wall is clearly pushing on me, right? I'm pushing on the wall's pushing back. Don't believe me? Well, what happens if I lean at 20 or 30 degrees like this? If I try to do this, I fall over, right? Because the wall's not pushing me to hold me up. The wall is what's holding me up here. So there's got to be a force of the wall pushing me, otherwise I would fall over. The action force is the hand on the wall. The reaction force is the wall on the hand. And since my hand is attached to my body, that force causes my entire body to stand up. My foot kicks the soccer ball. I'm not a soccer player, never was really. Even when I was a kid, I played soccer with my friends, but not anything organized. When I would kick a soccer ball as a kid, as a little kid, I would kick it with my toes. You're not supposed to kick it with your toes, right? It hurts your toes. Why? Well, because when your foot kicks a soccer ball, the action force is your foot on the ball. But the reaction force is the ball on your foot. Who plays soccer here? Nobody's a soccer player? When you kick a soccer ball, you're supposed to kick it with kind of the side of your foot, right? When you kick a soccer ball, you apply a certain force on the ball applies an equal and opposite force on you. It's not that you don't want to kick it hard, it's just that you want that reaction force to be on the side of your foot rather than on your toes, because you're more likely to hurt your toes with that same force. When a hand throws a ball, what's the action force? Well, that's going to be the hand on the ball. What's the reaction force? If I push on the ball with a force of 100, then the ball pushes back on me with a force of 100 in the opposite direction. It's going to be the ball on the hand. Now, explain this one to me. Why is it that if I'm standing right here on the floor, in the classroom on the floor, and I throw a ball forward with a certain force of 20 newtons, let's say, the ball pushes back on me with 20 newtons. The ball goes forward. Why don't I go back? 20 newtons is not a big force, right? It shouldn't cause me to accelerate at a huge rate because of my mass. But it should cause me to accelerate Some, shouldn't it? So the ball goes forward after a force of 20 newtons. Why don't I go backwards always? Sometimes I do. Sometimes I might. But why don't I always go backwards? Just with a lower acceleration than the ball. It goes back to something that we learned earlier on this unit. Because what? I'm heavier than the ball, okay, which means my acceleration should be a lot less than the ball, but it doesn't mean it should be zero. But yet when I throw that ball, if I'm playing baseball and I throw that ball, I don't go back at all. It's not that I just go back with a lower acceleration. I don't go back at all. Because your inertia, okay, you have a tendency to remain at rest, but still a force is going to cause you to accelerate, just not that much. Good. Braden's says it's static friction that's causing it. Let's say the maximum force of static friction between my feet and the ground is 50 newtons. We could calculate that, right? Fairly easily. SF max is equal to mu times the normal force. Let's say it's 50 newtons. Okay, I apply a force of 30 newtons on the ball. Ball accelerates forward, right? There's a force of 30 newtons pushing back on me, right? But static friction can be as high as 50. So how much is static friction going to be in this case? 30. The ball's pushing on me with 30 newtons. Static friction has to keep me from moving. So static friction is going to respond with another 30 Newton force acting on me so that the net force on me this time actually is zero because friction comes into play there as well. Does that make sense? If I applied a force of 40 newtons on a ball, would I move backwards? No, because static friction on me would be 40 newtons. If I applied a force of 60 newtons on the ball, would I move backwards? Yes. Yes, because remember the max force of static friction in that case was 50. So then I would move backwards and it would become kinetic friction at that point. Make sense? The reason you don't move backwards when you throw a ball is generally, at least, generally, the force that you throw the ball with is less than the max force of static friction between you and the ground. If it was greater, then you'd probably go backwards. And that's why if you throw a heavy ball when you're standing on ice, you might actually go backwards because the force of static friction is a lot lower. Next question? All right, let's state Newton's third law mathematically now. Mathematically, if we say object A applies a force on object B applies an equal and opposite force on object A, or we could say if object 1 applies a force on object 2 will apply an equal and opposite force on object 1. Do you see the notation I've used there? F12 is the force of object 1 on 2. F21 is the force of object 2 on object 1. So that second number that we've got there, that second number is always the object that the force is on. So the first one is the force on object 2, and the second one is the force on object 1. They're equal, but opposite, hence the negative sign there. The opposite means negative. Now we can also replace F12 with M times A. We'll call it M2 times A2 because it's the force on object 2 equals negative M1 times A1 because it's the force on object 1. You can see here by this equation that if M2 is bigger than M1, then A2 would have to be smaller than A1, which makes some sense, right? If I throw that light ball forward and it accelerates at a high rate, well, if I do accelerate backwards, I'm going to accelerate backwards at a low rate. Same force, but different acceleration because my mass is different. Let's take a look at an example here, right? One example, and then we'll give you a break for a second here. 75 kilogram man throws a 5 kilogram medicine ball. You guys know what a medicine ball is? Okay, those heavy balls that you use for something. The man accelerates backward at a rate of 0.25 meters per second squared. What's the acceleration of the medicine ball? Would you expect the acceleration of the medicine ball to be equal to the acceleration of the man, greater than the acceleration of the man, or less than? Greater than, because it's lighter, right? The force on the medicine ball is the same as the force on the man, always, no matter what. But the acceleration isn't the same. The acceleration will be greater. So let's say F12, here let's define first of all, let's define the man as object 1 and the medicine ball as object number 2. Let's say F12 is equal and opposite to F21. Let's say M2 times A2 is equal to negative M1 times A1. And now let's rearrange this to solve for the acceleration of the medicine ball, which is A2. Right? Medicine ball is object number 2. So let's say A2 is equal to negative M1 A1 over M2. Negative 75 kilograms. That's not a negative mass, right? You can't have a negative mass. It's just a negative in front of the whole thing. Times A1. The man accelerates backward at 0.25. We're going to make that negative 0.25 because it's backwards. Divided by M2, which is 5.0 kilograms. 75 divided by 5 is 15. 15 times 0.25 is 3.75, and it's positive because a negative times a negative is positive. All right, guys, we assigned worksheet number 15, questions 1 to 3. I want to take a look at 2 of those questions right now, questions 2 and 3. 2 says, a 70-kilogram man throws an 8-kilogram ball. The man accelerates backward. What's the acceleration of the ball? We're going to say that the man is object number 1 and the ball is object number 2. If we do that, then the force of 1 on 2, or the force of the man on the ball, is equal and opposite to the force of the ball on the man, F21. We're going to say M2 times A2. That's the net force on, once again, the net force on the man is equal to negative M1 times A1. That's the net force on the ball, which is, again, equal and opposite. The mass of the man is 70 kilograms. We know the acceleration of the man is 0.30, but backwards. So I'm going to make it negative. Okay, the mass of the man, the acceleration of the man, is equal to negative mass of the ball, which is 8 kilograms, times the acceleration of the ball. So we're going to solve for A here. 70 times negative 0.3 gives me negative 21. Negative 21 divided by negative 8 gives me 2 and 5/8, 2.625. Positive 2.625 meters per second squared, which is to 2 digits, 2.6 meters per second squared. How many people got 2.6 for that? Good, good. Now let's take a look at number 3. Harder question for sure. A 65-kilogram man throws a 200-gram ball. First thing I want to do is recognize that that's in grams, and I got to convert that to kilograms. The man accelerates backwards at a rate of 0.25. We want to know how fast the ball will be moving. Not the acceleration of the ball, but the speed or the velocity of the ball. We're going to call the man object number 1, and we're going to call the ball object number 2. You don't have to know how to solve this question. This is, in a small way, similar to the mother of all questions. In a small, small way. In that you don't necessarily have to know how to solve for the answer here. You could do something that you recognize from this question. Okay, well, you should recognize, hopefully, with what we've been doing over the last few minutes, that the force of 1 on 2 is equal and opposite to the force of 2 on 1. What's that going to get me? Don't worry about it. Don't worry about what that's going to get you. That's valid. We are allowed to do what's valid. So let's do it and get something and see if that helps us to get something else. F12 is M2A2 equals negative M1 times A1. M2, we already established, is the mass of the ball, 0.200. We don't know the acceleration of the ball. All right. The mass of the man is 65 kilograms. The acceleration of the man is backwards at 0.25. Does anybody have the value of A2 there? Positive 81.25, thank you. So the acceleration works out to be 81.25 meters per second squared, right? We just take the 0.2 over by dividing. All right, where are we going to go with this now? We just got something that we're able to get because we recognized a part of this problem. Doesn't mean we have our answer. So what are we going to do next? Nick, what do you want to do next?
I didn't do the next part, but I can try.
Okay. Now that we have acceleration, which we didn't have before, how are we going to find the final velocity? Yeah. Okay, so let's say A is equal to delta V over delta T. Luke, is that what you were going to say? A is equal to delta V over delta T. Rearrange it, solve for V. T goes up by multiplying. It's A times T. So we got 81.25 times the time interval here of 0.5 seconds. That's going to give me a delta V of 40.5 something, which is 41 meters per second. Now, technically, that's the change in velocity, not the final. But if the initial is 0, then isn't the final the same as what it's changed by? Yeah, so my final velocity here is 41 meters per second. Make sense? I want to do one more example with you, and then we'll wrap it up for the day here. The next example might not look like it's a Newton's third law question, and it's not in the same way as we just solved this one. But there is a thing at the end that ties in Newton's third law to this. We've got a system of masses here, a 20 and a 30, being pulled one way with 300 newtons and one way with a force of 100 newtons. These forces, by the way, are both what we call external forces. These are forces that affect the movement of this system. External forces. Remember, we used the analogy of the truck with the ice cream in it? The force between one ice cream bucket and the next ice cream bucket in the back of the truck, those are not external forces. They don't contribute to the motion of the truck, right? It doesn't matter what goes on inside the truck. The motion of the truck isn't changed by the forces that act between ice cream bucket and ice cream bucket. The motion of the truck is affected only by the external forces, wind resistance acting on the truck, the friction between the tires and the road in the truck, and so on, those external forces. The internal forces, the forces that act between ice cream bucket and ice cream bucket, or in this case between 20 kilogram box and 30 kilogram box, those don't affect the motion of the object at all. This is what we're trying to find for the first time, is an internal force. The force between bucket and bucket, or between box and box. So let's do this. The way that we solve this problem is to first analyze it like any other problem that we've done, and that is analyze the system. When we're analyzing the system, we're going to analyze only external forces. That's what we've done to this point, right? Is analyzed only external forces. We just haven't distinguished between external and internal until this point. But if you think back to all those questions we've done, remember the pulley problems? We didn't do anything with the rope. The rope pulled on the objects, the rope in between the objects, but we didn't use that because that was internal. We only used the external forces. So that's what we're going to do here as well. Analyze the system with the external forces. We're going to say F net is equal to the sum of the forces. We're going to call this force 1, force 2. So it's F1 plus F2. What's the tension in that rope that separates them? I don't know. I don't care right now. That's later on. Don't care. It's an internal force. You say M times A is equal to F1 plus F2. And mass is going to be 50 kilograms because we're analyzing the system. Times A is equal to negative 100 plus 300. So A is equal to what? 200 divided by 50, which is 4.0 meters per second squared. Look, the way we just solved this problem was as if the 20 kilogram and 30 kilogram mass were one object that weighed 50 kilograms. Does that make sense? You want to analyze the motion of a semi-truck. You don't analyze the back of the truck separately from the front of the truck, right? You analyze everything together as if it's one. That's what we just did. Now, we're not done yet. We're not done yet at all. We're halfway there. Now what I want you to do is analyze one object. Pick an object. I don't care which one. I don't care whether it's object number 1 or object number 2. Pick one object. This time you're going to analyze the internal and external forces. Let's pick the 20 kilogram object. If we pick the 20 kilogram object, we're going to say F1 is still 100 newtons. That's not changing, right? Because even if there's a rope joining the two objects together, if object number 1 is being pulled to the left with 100 newtons, yeah, sure, it pulls the system, but it also pulls individually that one object. But there's a force to the right as well. I'm going to call that Ft, force of tension in the rope. Like I pull the system with 300 newtons, the 30 kilogram mass pulls the 20 kilogram object with the rope. So there has to be a force in that rope pulling the 20 kilogram object. We're calling that Ft. These are my forces acting on the 20 kilogram object now. And now we're going to say F net is equal to the sum of the forces here, F1 plus Ft. Ma is equal to the sum of the forces, F1 plus Ft. What's M? 20, 30, or 50? What is it? Jenna, what is it? 20. Yeah, we're analyzing one object now. It's 20. The acceleration, anybody? 4. Like if the semi-truck is accelerating at 4, then all the ice cream buckets within the back of the semi-truck are accelerating at 4. Everything within that system is accelerating at the same rate. That's why we did that first part, was to get the acceleration. F1 is negative 100. Ft, that's what we're solving for. So 20 times 4 is 80. Take the 100 over to the other side by adding, and I get a tension force of 180, or 1.8 times 10 to the 2 newtons. Does that make sense? Now, I told you to pick one object, didn't matter which object. What would happen if I had to pick the 30 kilogram object? I would have done this. I would have said, here's my 30 kilogram object. Here's a force to the right of 300 newtons. Here's a tension force this way. I would have set it up the same way here, and I would have solved for a force of tension. What do you think I would have gotten? What do you think I would have gotten there if I had to analyze the 30 instead of the 20 kilogram object? Not quite. Yeah. Yep, exactly. Mass would change, but the mass would change. The net force here would also change. The tension wouldn't change, though. It would have worked out to be negative 1.8 times 10 to the 2. There's where Newton's third law comes into play, right?
Good afternoon, everybody. It is time
If the rope pulls with 180 one way on one object, it pulls with 180 the other way on the other object.